Hello, my shivering stars. Today, I, Shaurya Grover, welcome you all to this amazing platform of PW English. Students, I welcome you all to your Nexus batch, and today we are going to start with your new chapter, that is P block elements. Yes, students, you heard it right. We are with our last chapter of inorganic chemistry, that is P block elements. And after the students, your inorganic chemistry with class 11th is going to be finished. So students, how are we going to do this particular chapter? So as you very well know, in your class 11th standard, we do not have the complete P block. We have divided the complete P block, okay, into class 11th syllabus and into class 12th syllabus. So if I'm talking about class 11th syllabus, you will be holding your group number 13th and 14th over here. But if I'll talk about class 12th syllabus students, you will be having group number 15, 16, 17 and 18 of the P block in your class 12 standard. So this is the way how we are going to understand their groups, their properties one by one. Now when I'm saying in this particular P block chapter, in 11th, we'll be doing only the two groups, okay. That is your group number 13th and group number 14th. So we're going to start with that. Today I'll be taking group number 13, and in group number 13, I'm going to start with what are the elements, that means the introduction part. After that students, I will be focusing upon its properties, okay. The physical properties, the chemical properties, what are the trends, okay, with regard to ionization energy, electronegativity. So we are going to do all of this part in this particular session today. Okay. Now, what I feel is students, when we were doing, third chapter, the periodic classification of elements, in that particular chapter, when we studied about the periodic properties, atomic radii, ionization enthalpy, electronegativity, okay, and that is then was electron affinity. So when we studied, these properties over there, the same properties, the same trend that we did over there, the exception part is going to be used over here. Now, if you have done the S block elements chapter that we did before, you very well know what I am talking about, right? That means so many portion we have already covered in the third chapter. Now, students, if you have not seen that chapter, classification of elements and periodic properties, you will say, ma'am, then how we are going to do today? No need to worry. I'll be explaining you again all the terms, all the factors, whensoever, whichsoever is required over here. Clear everyone? Ready? So now we are going to start with this particular class. Now let me tell you students, basically this particular session is your lecture number 1 and the chapter name is P block elements. Okay, so we are going to start with this now. Let's proceed with the very first topic, but before that, ma'am, what are the segments that we are going to cover today? At least we should know, no, what we are doing, what is the sequence, right? So today's first of all, we shall be doing the introduction students. Okay, now in this introduction part students, let me tell you what exactly we are going to do. Now in this introduction part, exactly we'll be understanding that what are your, P block elements. What are your P block elements? Okay, that means we'll be explaining, that what is the reason that some of the elements are kept under the P block, why not under the S block, or why not under the D block, what is the reason behind that. So we'll be understanding about it. The next part after the introduction, we will be moving on to our boron family, towards boron family. Okay, and in boron family students, first of all, we'll be covering with the physical properties. We shall be covering with the physical properties, and after the students we shall be covering the chemical properties. What we will be doing, ma'am? We will be doing the chemical properties, right everyone? So basically these are the segments that we'll be doing in this particular class today. Okay, now let's start with the very first segment, that is basically the introduction part. Now in introduction part, let me tell you, I have told you that we have, categorized, the P block element students into which groups? Into group number 13th, into group number 14th, into group number 15th, group number 16th, group number 17th, and the last one is group number 18. Okay, so basically we have divided our P block elements into group 13th, 14th, 15th, 16th, 17th and 18th. Now let me tell you about them one by one. See students, the very first part that you should know about these groups over here, that group number 13th elements, what are the group number 13th elements? So it's basically boron, aluminium, gallium, indium and thallium. These are basically the elements that are present under the group number 13th category. That is boron, aluminium, gallium, indium and then comes the thallium. Coming towards what is your group number 14th elements? Which are your group number 14 elements? It is basically the carbon family. Okay. Now this is basically carbon, silicon, germanium, okay, and then we have Sn and Pb. So basically, now students, let me tell you, this is your carbon family, okay. Then comes group number 15, nitrogen family. Now from group number 15 to group number 18, this is in your class 12 standard. This is in your class 12 standard. Moreover, students, let me tell you, the general electronic configuration of all of them. What is the general electronic configuration of all of them? So basically, if I am starting with group number 13, its general electronic configuration basically is NS2NP1. NS2NP1. For group number 14, it's NS2NP2. For group number 15, it's basically NS2NP3. For group number 16, it is going to be NS2NP4. For group number 17, if you will talk about, it's basically NS2NP5. And for group number 18, if I'll talk about, it is basically NS2NP6. See, we very well know that p orbitals, there are 3 p orbitals and each orbital contains 2 electrons. So, total 6 electrons can be filled in the p orbital. That is what you can see. In group number 13, there is only 1 electron in the p orbital. In group number 14, there is 2 electrons in the p orbital. In group number 15, there is 3 electrons in the p orbital. In group number 16, there is 4 electrons in the p orbital. In group number 17, there is 5 electrons in the p orbital. And in group number 18, there is 6 electrons in the p orbital. This is what you can observe over here, right everyone? Now this is the general electronic configuration. Now the question comes, ma'am, where do they lie in the periodic table, right? So basically the p block elements, lie at the right hand side position, the right hand side position of the periodic table, If I'll ask you students, why are the elements kept under P block, are only kept under P block? Why not in S or why not in D? Why are they P block elements? Because you can clearly observe that the last electron in all of these cases is going to enter into the P subshell. Here it enters, see, last electron is 1 enters into P, it is 2 enters into P, and so on. You can clearly observe that the last electron enters into P subshell. That is why they are P block elements. So even you can mention this part over here, that the last electron enters into the P subshell. That is why it is called P block elements. That is why it is called P block elements. Now one more thing students, ma'am, here if you have written this is the general electronic configuration of the individual groups. So what is the general configuration for complete P block? So for complete P block students, it is going to be, now see, it is n minus 1 P from 1 to 6. then NS122. This is basically the general electronic configuration with regard to the p block elements. General electronic configuration of whom, ma'am? Of your p block elements. Now let me show you how do they look alike in the periodic table to justify your statement. Okay. Now see students, this is basically the periodic table that I am talking about. This is basically the complete periodic table that I am discussing over here. Now in the previous class students, we have done the S block elements. What were the S block elements? Hydrogen, lithium, sodium, potassium, rubidium, cesium, francium. The hydrogen we have covered separately, and after that we started from group number 1, lithium, sodium, potassium, rubidium, cesium and francium. The group number second elements were beryllium, magnesium, calcium, strontium, barium, and then comes the radium. These were group number second elements. Now I am talking about the P block, as these are S block elements. Now the P block elements I have already written is at the right hand side of the periodic table. So basically these elements are over here. These are your P block elements. Which one, ma'am? Group number 13th is boron, aluminium, gallium, indium and thallium. Group number 14 I already told you, it's carbon, silicon, germanium, then tin and then lead. So basically it's carbon, silicon, germanium, tin and lead. This is group number 14th. Group 13th, group 14th. Coming to group 15 to 18, if you want to know what are the elements, let me tell you, but that is under class 12 standard syllabus. Group number 15 is nitrogen family. So it is basically nitrogen, phosphorus, arsenic, antimony and bismuth. Then comes your oxygen family. So it's oxygen, sulfur, selenium, tellurium and polonium, right? Then comes your, halogen family. Fluorine, chlorine, bromine, iodine and astatine. These are your halogen families. Now comes your noble gases. Helium, neon, argon, krypton, xenon, radon. These basically are group number 18 elements. So from nitrogen family towards your last one, group 18, these are the part that we'll be doing under 12th class. We'll be only focusing now today over here in boron, about boron family and then about the carbon family. Coming back to my concept over here, students, let me tell you the other names that we give to, all of these. What are the other names that we provide? So group number 13 is also referred to as boron family. It is also referred to as the boron family. Okay. Group number 14 is also referred to as the carbon family. Also referred to as the carbon family. Group number 15, if I'll talk about, is referred to as your nitrogen family. It is referred to as nitrogen family. Yes, everyone. Group number 16, if I'll talk about, is referred to as your oxygen family. It is referred to as your what, ma'am? Oxygen family. Group number 17, if I'll talk about, these are your halogen family. These are your halogen family. These are your halogen family. And the last one, that is group number 18, is basically your noble gases. These are your noble gases. Clear, everyone? Clear, everyone? So these are the other names that we have given to this P block elements. Okay. Now talking about, students, the electronic configuration that we are going to start about. But I want you all people to at least write down each and everything that I've told over here so that we can start with the next part. Yes, everyone? Now, shall I move on to the next part? I feel, yes? Okay. Shall we, students? If you want students to me write down all the elements, I can write it down for your benefit. Okay, let's write down that as well. So that if you want to create notes, you can create it properly. So when I'm talking about group number 15, that's nitrogen, phosphorus, arsenic, then it basically antimony and bismuth. So students, basically these are the elements of your group number 15. Okay, now when I'm talking about group number 16, what are the elements? Now this is oxygen family. So it is basically, these are the elements, that is oxygen, sulfur, selenium, tellurium and polonium. These are present under the group number 16. Now let's talk about, students, the group number 17 that I'm talking about. So this is basically the halogen family. So that is basically fluorine, chlorine, bromine, iodine. Okay, these are the members of halogen family. Now let's talk about, the last part, that is the noble gases that we are talking about. So over here, okay, so basically this is helium, neon, argon, krypton and xenon. Okay, and then is radon as well. So basically helium is the one which is present at the top of neon, and it holds different electronic configuration. It holds basically the configuration of 1s2. Rest everybody continues with the same configuration as ns2 np6. So just don't get confused over this part. Okay everyone, now let's proceed to the next part. Here, talking about the next part, we have group number 13th as the boron family that I was discussing about. So what are the elements that are present under the boron family, students? Basically it's boron, then aluminium, then it's gallium, and then it's indium, and at last it's thallium. Right everyone? So I'm naming everyone over here. So it's boron, then it's aluminium, okay, then it's gallium, then it's indium, and at last that I'm talking about is your thallium part. So these are basically the elements that are present under the boron family. Yes, ma'am. Now let's talk about, students, their electronic configuration that I'm talking about. In order to remember the electronic configuration of all of them that I have discussed over here, students, there is a very short trick that you can go through. What is that trick, ma'am? That trick is basically, you can just add 8, 18, 18 and then 32. This is the short trick that you can follow. This is basically the magic numbers. Let me write over here. So if I'm talking about the magic number, so that basically is 8, 18, 18 and then it's 32. That we have to follow over here, right? Now coming back to my part over here. Now see, hydrogen, helium, lithium, beryllium, boron. You should remember the very first element's atomic number. So boron has an atomic number, ma'am, 5. Now what is the next part you're going to do? You're going to just add these values over here. So 5 plus 8 comes out to be what, ma'am? 5 plus 8 comes out to be 13, ma'am. Now 13 plus 18 comes out to be what, ma'am? 13 plus 18 I'm talking comes out to be what, ma'am? It is basically, ma'am, 31. Now 31 plus 18 comes out to be what, ma'am? It is basically, ma'am, 49. Rest, right? 49. Now then 49 plus 32 comes out to be what, ma'am? It is 81. So basically these are the atomic numbers of the element that I am talking over here. Yes, students, let me show you in the periodic table also so that you won't get confused. See, basically, it's 5, 13, 31, 49, 81. So, if you'll apply the same rule for the other, groups also, you're going to get the same answer. Let's do that. Yes. Okay. So, basically, let's start with the carbon family. Now, one thing what you can do is either you can just add 1111 number and you can, tell the other elements atomic number. But if not, you can go through that way. If you feel like, ma'am, for that, first of all, we have to write one, group's atomic number and then we have to go on to the next one. So what you can do is over here, it's a very simple thing that you can remember is just go with the magic numbers, that is 8, 18, 18 and 32 respectively. So if you remember this magic numbers, you can write down the electronic configuration of any group of any element you may know, right? And you will not forget also. Now students, see, if you know for carbon it starts with, its atomic number is 6. So again go with 8. So it's 6 plus 8 that comes out to be 14 and then 14 plus 18 comes out to be 32, right? Now see, 32 plus you're going to do add 18, it's 50. 50 plus 32 is 82. Simple way. In the same way, see, for nitrogen family, we are starting with atomic number. We know is nitrogen is 7. See students, let me tell you, let me clarify it very firstly. Whensoever you are learning the periodic table, at least learn, the first 30 elements name. okay, and with atomic number obviously, so that you, if you forget any other elements, at least if you know once, you can calculate for the other part, right? Coming back over here, let's see for nitrogen now. Nitrogen basically, if it has 7, we very well know. We are going to add 8, now it comes out to be 15. Then we are going to add 18, what it is coming out to be? It will come out to be 33. Then 33 plus 18 comes out to be what? 51. Then 51 plus 32 comes out to be what, ma'am? 83. Simple. So now see how you're going to tell the atomic numbers of each and other elements very easily, right? Let's see in the oxygen family. Again, we'll go with the same flow. 8, 18, 18, 32 respectively. So oxygen, its atomic number is 8. Let's add 8. It comes out to be 16. So sulfur has atomic number 16. Now just add 18. You will get what, ma'am? 34. Add again 18. You will get 52. Add 32. You will get what, ma'am? 84. Simple. Easy. Okay, let's see now the the halogen part. 9 plus 8 is 17. 17 plus 18 is 35. 35 plus 18 is 53. 53 plus 32 is 85. Simple. Let's see the last one now over here. Now in this part it's different. Let me tell you, for the last one it's different. For group 18 it's different. What it is, here you have to use another rule. What is that, ma'am? It's basically 8, 8, 18, 18, 32. Now you have to go with 8, 8, 18, 18, 32 in that way. Yeah. So basically over here it's 2 plus 8 is 10. 10 plus 8 is 18. Then again you have to add 18. So 8, 8, now 18, 18. So 36 plus 18 is 54 and then add 32, you'll get 86. Clear? Easy way? Okay, ma'am. Okay, ma'am. Let's now, move on to the next part, students. Moving on to the next part, we have already discussed about electronic configuration. So let's delete the slide. Now we're going to start with the atomic radii. Atomic radii, if I'll talk about, students, is a very important topic over here. Now in atomic radii, first of all, let's write down all the elements. And for this part, what I have done is, students, here I have brought the NCERT key highlights also. Now why I have done that? Because I have already told you that inorganic is something where we need to read NCERT, right? So what I feel is, like in S block elements also, I have taken some of the NCERT highlights, but I have felt that you are not reading NCERT on your own. So some of the key points which I feel like are important and to be written or to be highlighted, I have written over here so that you can mark it over there. Coming back over here now, see, students, as I've told you that in atomic radii, first of all, let's write down all the elements. So we have boron, aluminium, then it's gallium, then it's indium, and then it's thallium. Simple part, no ma'am, simple easy part. Now let's see over here, students, when we have this topic over here, boron, aluminium, gallium, indium, thallium, we have written the elements. Now what generally happens when we go from top to bottom? What do you feel, what is going to be the general order when you're moving from top to bottom? Ma'am, it's very easy. What is easy over here? That when, ma'am, we move from top to bottom, number of shells are increasing. What happens over here, ma'am? Number of shells are increasing. If number of shells is increasing, the distance from the center to the outermost shell electron will automatically increase, right? And if the distance from the center to the outermost shell electron is increasing, that means atomic radii is increasing. Ma'am, how can I say that? And ma'am, one more thing, ma'am. In the previous part, we have written atomic numbers, but not the electronic configuration. So coming to that part also, let's see. Let me write it over here, right? Let me write over here. Now we very well know the general electronic configuration. First I'll tell you this part only, then we'll move to that part. So it's NS2NP1. This is what I've told you. Now N, students, here represents the shell number. N represents the shell number, right? Now if I talk about the boron case, here N value basically is going to be what? It lies under which period, ma'am? It lies under the second period. It lies under the third period, it lies under the fourth period, it lies under the fifth period, and it lies under the sixth period. Let's see how I can say that. See, if I have to write the configuration of boron, it's a very simple. As per the Aufbau rule, we are going to write the electronic configuration, no, students. So let's see, students, now in this case, I am writing generally, not according to that part. So if it is 5, it is going to be 1s2, 2s2, 2p1. Let's count the electrons. 2 plus 2, 4. 4 plus 1 is 5. Yes? Okay. Now let's write for aluminium as well. So it is going to be 1s2, 2s2, 2p6. Now see, 3s2, 3p1. Yes, this is for what? Aluminium. Let's count. 2 plus 2, 4, 4 plus 6, 10, 10 plus 2, 12, 12 and 1 is 13. So it's 13. Now, what is the thing that I want you all to observe? See, this is the outermost shell, the second shell. Here, this is the outermost shell, the third shell, right? So, the outermost shell contains how many electrons? It will have this general configuration, ns2 np1. It will have this general configuration, just see. It is basically 2s2 2p1. It is basically 3s2 3p1. That means for gallium, what it is going to be when you're going to put the value of n? It is going to be, ma'am, 4s2 4p1. What it is going to be here? 5s2 5p1. What will be it over here? 6s2 6p1. That means the things that I'm writing over here, this is for the outermost shell electronic configuration. Outermost shell electronic configuration. Yes, everyone. Clear, everyone? Okay, now let me draw the structures also in order to clarify it more properly. Coming back over here, when I was talking about, I have boron, I have aluminium, I have gallium, I have indium, and I have thallium. I am telling that from top to bottom, students, if number of shell value is increasing, atomic radii should increase. Atomic radii should increase. This is what I am saying. Okay. According to that process, why I am saying this, first of all, let me explain you over here. See, if I am talking about boron, boron basically has 2s2 2p1. Aluminium basically has 3s2 3p1. Gallium basically has 4s2 4p1. Indium basically has 5s2 5p1. Thallium basically has 6s2 6p1. Now, when I'm drawing the structures over here, just observe in the case of boron. This is my nucleus, my first shell and my second shell. Second shell contains, 3 electrons in the outermost shell. Okay, let's talk about aluminium. If it is my nucleus, my first shell, my second shell, and this is the third shell for the case of aluminium, because it is 3s2 3p1. Let's talk about the next part, that is the gallium, students. So basically it's 1, then it's 2, then it's 3, and then it's 4, students. So automatically, what are we observing? What exactly is atomic radii? The distance from the nucleus to the outermost shell electron. Right, like this. This is what is an atomic radii, and we can clearly observe that radii is increasing. So what exactly should be the order? The order should be like this. It should be like this. It should be like this, but let me tell you, it is wrong. It is wrong. There is an exception. This will be wrong for the case of boron family. For p block element, students, order is going to be different. That means, ma'am, exception part. Yes, everyone. Now comes the exception part. What exactly is the exception, ma'am, that you are talking over here? Let me tell you, students, there is an exception that you're going to observe between aluminium and gallium, that they will have different values. Yes, ma'am. That means aluminium is going to have more value than gallium. Let me tell you basically what. Okay. Moving down the group, for each successive member, one extra shell of electron is added, and therefore atomic radii is expected to increase. This is what I've shown you, right? However, a deviation can be seen, right? So now highlight it and write it. There is an exception, so that whensoever you are studying this part, you will read it properly. You won't skip that topic. Yes, now what is that exception, ma'am? Let's talk about it. See, atomic radii of gallium is less than that of aluminium. I told you, that the trend of, gallium and aluminium is going to change. There is an exception over here. Okay, now what is basically that exception? Let's understand it. Let's understand it, students. Now, there is one term, that is poor shielding effect. There is a term, that is poor shielding effect, and as per poor shielding effect, S basically, let me tell you about the shielding power. S has highest, then P, then D, and then F. So D basically has poor shielding, D basically has poor shielding. And when you come And when you come at gallium, here d orbitals basically start to fill, because see, till aluminum we only fill till p orbital, but when you come at gallium electronic configuration, d orbitals come, and d orbital basically has poor shielding effect. Now when something is a poor shielding, what exactly it is, ma'am? First of all, explain us. For example, I am nucleus, I have, first shell, second shell, third shell and fourth. What happen is, for example, one electron from the outermost shell is coming inside, so the inner electrons are basically applying the force, the negative electronic repulsion force, so that electron cannot come inside. That is what is the shielding. Okay, so d orbitals have very poor shielding, they cannot protect the nucleus, okay, so that the outermost electron can come. They cannot protect it properly. So what happens is, the outermost electron comes and the atomic radii will decrease. That means at the entry of the d is shell over there, atomic radii will decrease. So gallium's radii will decrease, and hence the order is going to be changed. Here boron comes, okay, then basically it is gallium, then it's aluminium, then it's indium and thallium. So basically this will be order over here. The order that you're going to observe, the atomic radii of gallium is less than that of aluminium. This can be understood from the variation in the inner core of the electronic configuration. What is that? Presence of additional 10d electrons offer only the poor screening effect. Due to the poor screening effect, there is a change, there is an exception that we observe over here. Hence the order comes out to be different. Now students, coming to the next part, that is ionization enthalpy. Let me first explain you students what exactly is ionization enthalpy. So ionization enthalpy students is basically the minimum amount of energy, the minimum amount of energy, the minimum amount of energy that is required to remove one electron from the outermost shell of an isolated gaseous atom. This is what is an ionization enthalpy. The minimum amount of energy that you give in order to remove one electron from the outermost shell is the ionization enthalpy or ionization energy. Usually students, it is represented as IE. Okay, now coming to the ionization energy concept over here, how you're going to do it, how you're going to remember it. Okay, so basically it's a very simple trend, that is W that you have to follow over here. This is what is W that you're going to follow over here. Let me tell you, first of all, let's read from NCERT to explain it clearer, and then I'll write everything. The ionization enthalpy values are expected for the general tens do not decrease smoothly down the group. Now let me tell you what are they talking about, okay, so that you can get an idea. See, first of all, this is the exception that I'll give you an idea. First, let's see what is the general thinking about ionization enthalpy. See, if it's, boron, aluminium, gallium, indium and thallium, when we are students moving from top to bottom, we say that number of shells are increasing. This is general thing that we say, and we say size is increasing. If size is increasing, ionization energy should decrease. Why? The very first thing that you should know is ionization energy is inversely proportional to size. This thing everyone should know. Why, students? Just understand it. For example, in a case I am saying that the atom size is very small. If an atom size is small, that means it is close to nucleus. Now nucleus is a positively charged species, right? And if the size is small, it is holding that electron strongly, because the size is small, force of attraction will be larger. Now let's consider if the size is large. If size is large, there won't be that much force of attraction, that is, at the initial part when the size is small. Okay, so minimum, if you'll give minimum amount of energy and very less energy, in that case, electron can be liberated very easily. But in the case where size is small and force of attraction is higher, no, you have to give a lot of energy to remove the electron. That means ionization energy when size is smaller is basically the higher. That means on increasing down the group, when we see size increases, ionization energy will decrease, because it is inversely proportional to size. Now as per this, we say that it should basically decrease, but but this is the wrong case. This is the wrong case. Why? There is an exception. What is an exception? What do you see over here? Basically, this is with this will be the order. This is boron, aluminium, gallium, indium, and then thallium. By this way, you should remember the order for the ionization enthalpy. Students, I would say first of all, write down the things that I've written over here, because all of these things I've explained in the third chapter, though I am explaining it over here again. Till then, I'll drink a glass of water. Everyone just write down this concept that I have written over here. Now, coming to what I'm explaining over here as W, just extend it a bit over here like this. Yeah. So the order is going to be like this: boron, then thallium, then is gallium, then is aluminium, and at last is indium. So basically this is going to be the order, and this you can learn with the help of a W that I have created. This is the order. So they say observe discontinuity in the ionization enthalpy values between aluminium and gallium and between indium and thallium are due to inavailability. Now what they're saying is, they are saying that here you can see between gallium and aluminium there is a change that you can observe, that gallium has more than aluminium. Why is it so? Because here there is an entry of d orbital in gallium, and why in indium and thallium there is a change? Due to entry of the f subshell, and D and F both have poor shielding effect. That's why, students, so which have low screening effect to compensate the increase in nuclear charge. So this is going to be the order. Everyone just write down the order so that now we can move on to the next part. Everyone just write down the order so that now we can move on to the next part. Done? Yes, that's great. Now students, we're going to start with the electronegativity concept. We are going to proceed with the electronegativity concept, and let me tell you about electronegativity. This is basically the tendency to attract shared pair of electrons towards itself. This is what is electronegativity. Electronegativity is attracting a shared pair of electron towards itself. Let's say if I have two, atoms connected A and B, and I say that B is more electronegative than A. So it's very simple part. If it is more electronegative, it will gather a partial negative charge, and A will gather a partial positive charge. Yes, everyone. So this is what is electronegativity. That means the electrons of this bond are close to B in comparison to A. Though they are sharing between both of them, but it is slightly more towards that part. Yes, everyone. Clear with this thing now? Now, talking about this concept, let's see basically what I'm talking about over here. I have told you that electronegativity trend, okay, is basically very simple. It will be inversely proportional to size, okay. So basically when I'm talking about boron, aluminium, gallium, indium, thallium, it should be again like this. From top to bottom, ma'am, size is increasing, so electronegativity should decrease. But this is again wrong. There is again an exception. So basically you have to learn it like this. If it is boron, okay. Now, this is again the same part. Boron, aluminium, then comes gallium, indium, and then the thallium. Basically, this is the trend that we are going to see. Boron, then thallium, then indium, then gallium, and at last aluminium. So this is going to be the trend for electronegativity. Everyone just write down, this is an exception for the electronegativity. Everyone just write down the exception for electronegativity. Done, 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 done. Okay, now students, there are few more physical properties that we need to talk about. Okay, starting with density. So density, always remember, this is basically the order for density. That density down the group is going to increase. Density down the group is going to increase. The very first part. Density down the group, simple, is going to increase down the group. This is a symbol of increase. Remember, when you're moving from boron, aluminium, gallium, indium, thallium, density is going to increase, ma'am. Simple part, easy. Okay. So students, now we have seen basically the order of density. That density is going to increase, right everyone? Now let's talk about, the melting point and the boiling point. See students, the boiling point order that I'm talking about over here is very simple. Ma'am, boiling point is going to decrease down the group. Boiling point order will be that it is going to decrease down the group. Okay. Now what about melting point? Its order, students, is quite different. First of all, melting point decreases till gallium and then increases after that. So basically, if I have to write all the elements over here, I can say boron, aluminium, gallium, indium, thallium. I have this part. Right. Now, first of all, it is going to decrease and then it is going to increase. So, in actual, if it is going to decrease, boron will have highest, then aluminium, and then it is going to be thallium, and then indium. At last, it is going to be gallium. This is the order for melting point. If boiling point order, students, you want to write, it's very simple. It decreases down the group now. So, when it decreases down the group, higher will be of boron, aluminium, gallium, indium, and thallium. This is for your boiling point. Everyone, just take a look and write down both the orders over here. Just take a look and write down both the orders completed with this part. So let's read the other physical properties now. Boron is a non-metallic in nature. It is extremely hard and black colored solid. Remember that. It exists in many allotropic forms. Due to the very strong crystalline lattice, boron has unusually high melting point. Yes, now. Rest of the members of soft metals with low melting point, we've clearly seen that, and high electrical conductivity. Then the density order and then melting point, boiling point order already told you. That's great, students. Okay. Now, students, we shall be starting with the chemical properties with regard to the boron family. Okay, ma'am. So here, first thing that is still left, that is oxidation state. First of all, let's discuss it. Oxidation state. So talking about oxidation state, what exactly is oxidation state or oxidation number? Students, it is basically the formal charge that is present on any atom, or I would say the element. On any atom, or I would say the element. Yes. Now see students, this is what is an oxidation state that I'm talking about, right? Now if I'm talking about boron family, boron, aluminium, gallium, indium, thallium, these are my members of the boron family. Now when you move from top to bottom, +3 oxidation state, stability will decrease down the group, and +1 oxidation state stability will increase down the group. What exactly it is, let's understand, students. That means if I have to write boron, aluminium, gallium, indium and thallium, if boron is present in +3 oxidation state, it is quite stable. Aluminium in +3 is very stable. Gallium also. Indium basically can exhibit such oxidation states, and thallium only +1. That means if I have to create a compound BCl3, that is possible, but TLCl3 is not possible. Compound with thallium basically is not possible. Only TLCl is possible. Why is it so? Why is it so? See, here in this state, we can say that boron acquires a +3 oxidation state, and we know chlorine acquires a -1. So BCl3 can be formed. But thallium cannot exhibit +3 oxidation state. It can only exhibit +1 oxidation state. Due to which I am saying if thallium has +1 oxidation state, Cl has -1, and if I have to create a compound, it creates TLCl. So that is possible over here, students. That is the tendency that can take place. So ma'am, now question comes that why do we can see that they both are stable in +1 oxidation state, why not in +3 oxidation state? Now the reason behind this is due to inert pair effect. Due to inert pair effect, this happens. Now, what exactly is inert pair effect? Inert pair effect is tendency of the inner electrons tendency of the inner electrons to not participate to not participate in bonding. To not participate in bonding is basically the inert pair effect. That means if I'm saying they have a general configuration as ns2 np1. Now in the case of indium and thallium, the ns2 electrons, the inner electrons won't participate over here. They won't participate in bonding. Only one electron will be participating, hence the oxidation state comes out to be +1 for that case. Clear everyone? So this was all about oxidation state. Now students, we are going to start with the next chemical property. It's a request to each and every one of you to please first of all kindly write down everything that you have written over here. Now we can move on to the next part, that is reaction with oxygen and formation of oxides. Reaction with oxygen and formation of oxides, everyone. Yes, so here the next chemical property is reaction in with air, or I would say with O2. Now, in general, if I'll talk about, let's skip boron. I will tell you about boron afterwards. Let's talk about, the other elements. So, I'm considering element as E. I know that elements have +3 oxidation state. Oxygen has -2 oxidation state. So, which kind of compounds can be created? E2O3 compound can be created. That means when our elements of boron family combines with oxygen in the air, that means in the presence of air, if this reaction occurs, it creates which kind of a compound? It creates E2O3. It creates what, ma'am? It creates E2O3. Clear everyone? Clear everyone? Yes everyone? Okay, now other thing you should write over here, that impure boron reacts with air to form oxide but pure boron does not do that. Pure boron does not form oxide. Everyone just write down, very important key highlight. Then we'll talk about aluminium. Now you will ask me, ma'am, you have written that it is, it cannot react in the presence of air. Why is it so? Because it will, if it reacts, the pure boron, it will be less reactive. That's why it is not stable. Sorry, it is less reactive, that's why it cannot be created. Now talking about aluminium, let's write down about aluminium. Aluminium, students, creates a layer of oxide on its surface. On reaction with air. So when it reacts with air, aluminium creates a surface of oxide, a layer of oxide on its surface. It creates a layer of oxide on its surface. Clear everyone? Just write it down. Students. Everyone, just write it down so that now I can do the next reaction part. This was reaction with air. Now we are going to move on to the next part. Let's say reaction with halogens. Let's talk about the reaction with halogens. Now it's a very simple thing, students. Our element E here stands for, the boron family that I'm talking about. All the elements of boron family, the group number 13. When it reacts with X2, it forms what? It forms EX3. What it forms exactly? It forms EX3. Clear everyone? EX3 is created. X over here is fluorine, chlorine, bromine, iodine, and all of this basically exists in the diatomic form, F2Cl2Br2I2. That's why I've written it like this. And how it is done, you very well know. E is +3, X is -1, so basically it's EX3 that is created over here. Everyone clear with this part? But exception exception of thallium, it cannot form because thallium has +1 oxidation state. So it can form TLX. It can form TLX because it exhibits +1 oxidation state. And what is the reason, ma'am? Due to inert pair effect. Due to inert pair effect. Everyone just write it down. Now coming to the next one. Coming to the next one, what do we have with us? What do we have with us? We are going to react it with some acids such as HCl, H2SO4, and let's see what we are going to form. Okay. Reaction with acids. See now, if aluminium, students, reacts with HCl, what it is going to form? AlCl3, liberating H2. Simple, no? If it is reacting with H2SO4, what it is forming? Al2SO4 thrice. What it is forming? Al2SO4 thrice, liberating water. So this is basically the reaction with acids. Everyone just write it down. Everyone just write it down. Moreover, if you balance it out here, SO2 will also be released. Right? Then you have to balance. If you balance it out, basically these are the byproducts that are created over here. This is basically the reaction with acids. Now students, I'm giving you some questions over here as a homework. Okay. Let's see whether you are able to do them or not. So I'm writing some of the homework questions over here for you people. Okay. So I'm mentioning some of the homework questions. Yeah. So first homework question, students, for you people is an element that exhibits negative oxidation state in group number 13th is. Just try to find out, read NCERT, otherwise I'll let you know. The second is, among group number 13th, the element with highest ionization potential, that means ionization energy, and lowest ionization energy is what? Okay. And lowest ionization energy is what? Now, question third, the element whose atomic volume is least is, now this is also among group number 13 that I have written. Okay. And the last is, which of following pairs have same atomic radii? Same atomic radii. Now that's aluminium and gallium. Second is magnesium and aluminium. Third is beryllium and magnesium. And fourth is boron and beryllium. Now students, this is all about the homework part that you have to do. Everyone just write it down. Clear with this segment? Clear? That's great, students. Now students, we are ending our today's class over here. The homework questions will be discussed with the homework questions of S Block Elements chapter in the next session. That is going to be tomorrow. So as it was an introductory part, we have covered basically the general properties with regard to the boron family, that what are the physical properties, what are the chemical properties, that we have clearly mentioned, we have clearly discussed. Now students, it's time for you to start reading NCERT. See, I have not given so much topic today because it was an introduction to P Block Elements. So you can go, 2 to 3 pages read NCERT NCERT daily, that would help you out. You have been, you are able to understand over here very clearly. Now it's time to read and, brush up your concepts. So start solving questions that I've given as a homework, because tomorrow's session, initially we'll be understanding all the homework questions only first. We'll be finding out answer for the homework questions, and then we will proceeding to the next part. Clear, everyone? So now students, I will be meeting you in the next lecture. Till then, keep smiling, keep learning. Thank you so much, and I have a good day, students. Take care of yourself.